We can get started. Great, thank you. Thanks for the recording. Welcome everybody to Design Safe webinar today. This is our last Dataset Award winner webinar, so I'm really excited to be here with you. I just wanted to make a few announcements here before we introduce our speakers and get on with the main event. First of all, we have nominations open now for the 2023 Dataset Awards. This is basically for any project that was published in Design Safe during the 2022 calendar year. So if you know of a good project, feel free to nominate it. You can find it right there on the front page of our website. And you can also find all sorts of useful information. Here's a link to the webinar today, right? Experimental study of the wind effects on transmission systems via aeroelastic testing. I'm Scott Brandenburg, professor at UCLA. So good morning, I guess, from California, probably good afternoon for most of you. And I'm part of the Design Safe team here, working on the ECO activities. I just want to remind everybody we do have a survey. So we look at survey results to get feedback from the community and improve these webinars. So here's a QR code. Feel free to scan that and do the survey. I'll show it again at the end of the webinar, so don't feel like you have to capture it right now. It'll be back again. All right, and I will now move on to introducing our speakers. Today we have with us Ziad Aziz, who began his career as an adjunct professor at the Lebanese American University in Beirut, and is currently an adjunct professor at FIU, working at the Wall of Wind. And then we have Ashkan Jeddi, who has his bachelor's in civil engineering from the Iran University of Science and Technology in Tehran, and master's in structural engineering from Sharif University, and works at risk assessment and management, and is currently a graduate research associate at Ohio State University. So they're going to talk to us today about wind effects on electric power transmission. This is a really important area, especially in coastal areas, because our power infrastructure faces significant risk from hurricanes when exposed to strong winds. Demands in the elements in the transmission tower line systems may exceed the capacities and trigger various modes of failure. And they've done a great job with documenting some experiments at the Wall of Wind on these systems. And so I will stop my share and turn it over to them at this point. And as I'm doing that, I would just like to say, if you have questions for them during the presentation, there's a Q&A feature at the bottom, and it's different than the chat feature. So we would prefer that you use the Q&A. It's easy to keep track of which questions have been answered and things like that. And they may type questions as we go, or else I'll moderate questions at the end. So with that, Ziad, the floor is yours. I can see your screen, so you're all good.
Thank you. Good afternoon, everyone. My name is Ziad Aziz, and together with my colleague Ashkan Jeddi, we'll be presenting the proposal that was granted to us by NSF to work on for the past 4 or 5 years, which is entitled Experimentally Validated Stochastic Numerical Framework to Generate Multidimensional Fragilities for Hurricane Resilience Enhancement of Transmission Systems. So the presentation will be divided in two. I'll begin by discussing the aeroelastic testing to evaluate the wind effects on transmission line systems, so mainly the experimental side of the project. And I'll give the floor to my colleague Ashkan to discuss the estimation of the drag coefficients and gust response factors on a lattice tower, which is more the modeling side. So let me begin again. So I'll discuss the experimental side, the aeroelastic testing to evaluate wind effects on transmission line systems. So that was my PhD dissertation when I was still studying at FIU. At the moment, I'm a senior forensic engineer, and I'm also an adjunct professor at Florida International University. The collaborating authors for this project are Dr. Amal Al-Awadi, Dr. Arindam Gan-Chowdhury, and Dr. Peter Irwin. I'm going to discuss briefly the outline of the things I'm going to go over. So why this topic is significant and the knowledge gap, the aim of the project, the central hypothesis behind it and the test phases, the methodology, how we estimated the damping, some conclusions and other results, some of the published work, and how to utilize the data from the NSF Design Safe website. So 87% of all US power outages are triggered by severe weather, which makes them the leading cause of blackouts. Losses were estimated at $55 billion between 2003 and 2012. And there's considerable consequences of failure and multiple failure modes, as you can see in the picture below, where you have multiple modes of failure among failure of tower body, failure of tower legs, pull out of the foundation, rupture of the conductor, damage to the cross arms, cascading failure of the cage and the cross arms, as well as cascading collapse of the towers. So why are transmission lines vulnerable? Because the failure of one tower can lead to the cascading failure of other towers in the line, which creates a domino effect. Conductors could be dynamically excited by the natural wind due to a very low aerodynamic damping at very low wind speeds. The design standards currently, they tackle the along wind response only of the transmission lines and the transmission towers. Although several researchers in the past noted the importance of including crosswind as well as torsional responses. So this NSF funded project is a joint collaboration between Ohio State University and Florida International University. This effort aims to fill the current gap in knowledge by conducting an experimental program to study the aeroelastic response of a multi-span transmission line system subject to hurricane winds. The results will provide deeper insight into the highly complex coupled dynamic behavior at system levels. So this was the part that was taken care of by FIU. And this project also will enable the validation of critical aerodynamic and aeroelastic responses generated by a finite element model, which Ashkan will discuss later on. So the central hypothesis is that an experimentally validated stochastic numerical modeling platform can help number one, generate multi-dimensional fragility surfaces, which can be used to estimate with high level of confidence component and system level failure probabilities. Number two, derive cost-effective upgrades. And number three, implement new design solutions. So the experimental test phases were divided in three. The experimental work followed a total of 3 phases. The aeroelastic testing of a self-supported lattice tower, so one tower by itself. Then an aeroelastic testing of a multi-span transmission line system, which consists of 3 towers, 4 spans of conductors, and 2 end frames. And number 3, the effects of the conductor or insulator rupture on the behavior of the transmission line system. So for the methodology, what are the advantages of using an aeroelastic model? Number 1, the influences of the mode shape and their interactions can be well incorporated. There's better simulation of the turbulence effects without the need for mathematical extrapolation, and it can correctly mimic the dynamic response at small scale. However, it's kind of challenging to do an aeroelastic model, and some of the most important features to preserve are the drag forces, the mass, the frequency, the aerodynamic damping, and the exact properties of the natural wind. So as you can see on the right side, this is the full transmission line model that we tested. We've used Froude number scaling, which characterizes the ratio of fluid inertial forces to gravitational and elastic forces of the structure itself. The scaling is simply achieved by linking the velocity scale to the square root of the length scale. For this project, we chose a length scale of 1 to 50. So the velocity scale would be 1 to square root of 50 or 7.07. The complete transmission lines model consists of 3 towers, 4 spans of conductors, and 2 end frames. So to fit that entire model on the wall of wind turntable, which is approximately 16 feet in diameter, a horizontal distortion technique with a scale of 1/3 was further implemented, which transforms into a length scale of 1 to 150 for the conductors only, for the length of the conductors. The concept revolves around maintaining the same sag while preserving the properties of the initial model, which are the mass, the drag, and the frequency. This is particularly feasible because the natural frequency of cables is a primarily function of their sags if the tension is not high, which is the case of conductors in transmission line systems. Other parameters to maintain: the new length scale for the conductors, which is 1 to 150, the new mass per unit length, and the new drag forces on the cables. Some of the imported scaling factors to maintain are the length, obviously 1 to 50, the velocity 1 to square root of 50, the mass 1 over 50 power 3, the damping, which is 1, the acceleration is 1, and the elastic stiffness, EI, which is 1 over 50 power 5. So how we build the actual steel tower. So it's a steel self-supported double circuit vertical lattice structure. It's a discrete aeroelastic model which consists of a spine, which models or mimics the structural properties of the tower itself, and non-structural cladding elements, which are the 3D printed elements you see in white, and that they maintain the aerodynamic shape of the tower itself. These are some pictures of the finished tower. These are some pictures of the finished or the entire transmission line system. Though this is this was phase 1, this is phase 2, and this is phase 3. So in phase 3, we decided to cut one insulator and determine how it will affect what are the effects on the transmission line itself, and also cut one conductor and see what are these effects. So for the validation, we did a validation on SAP 2000 for the design at the beginning. So for the spine only model and for the full model itself, we checked for the main modes of vibration, where you have the highest mass participation ratios, and the percentage difference between the model frequencies and the target frequencies were about 2.6% at most. For the instrumentation, we've used 3 6-degree of freedom load cells, which were installed at the base of the spines or the transmission towers. We've used 3 accelerometers on the middle tower, and we've used 20 strain gauges, which were attached on various parts of the cross arms and the spine in order to measure moments and drag on the conductors themselves. So the model was tested at 4 wind speeds, 5, 7, 9, and 11 meters per second. This is at small scale, which translates to 35, 50, 64, and 78 meters per second at full scale. The models were rotated between 0 and 90 degrees at 15 degrees increments. As you can see in the picture, in the diagram, the 0 degrees is along the strong axis and the 90 degrees is along the weak axis of the tower. The duration of each angle exposure is about 2 minutes, which translates to about 14 minutes in full scale. And we've used open terrain exposure as well. Now I have a small video here taken from the single tower test. As you can see here, the main mode of vibration is along the weak axis with slight response in the crosswind direction. I also have a small video from the entire model. As you can see here, the main mode of vibration is galloping and vibration of the conductors themselves, and it's mostly a buffeting behavior or response. So to estimate the damping, we've used the iterative least square and the random decrement techniques, which were used on the acceleration data in order to obtain the total damping. The previous techniques were also utilized on free vibrations of the tower model in both strong and weak axis. So we did that estimation twice, one with the wall of wind fans turned on and one with the wall of wind fans turned off. So when we free vibrate the model, when the fans are off, we will get the structural damping. When we free vibrate the model, when the fans are on, we will get the total damping, and from that we can obtain the aerodynamic damping. We've compared those experimental techniques with the along wind aerodynamic damping of lattice structure, which was given by Loredo Sousa in 1996, which is mainly a function of the tower height per zone of tower. It includes the mean wind speed, the drag coefficient, the width of the zone, the mode shape, the mass, the frequency of the mode shape, and the density of air. So for the damping estimation, considering along wind at 0 degrees, which is the strong axis, we've obtained good results at higher wind speeds. Between the analytical and both experimental techniques. But we've obtained even better results in the along wind at 90 degrees for both ILS and random decrement techniques with respect to comparing them with the analytical model or analytical equation. For the crosswind, as I previously mentioned, there's no analytical equation derived to obtain a crosswind damping of lattice towers. Therefore, we analyzed the component of the accelerometer, which is a crosswind acceleration, and from that we applied the ILS and the iterative least square and the random decrement technique to obtain like a certain estimate of the crosswind aerodynamic damping. And as you can see, at 0 degrees, the crosswind damping at 0 degrees at small wind speeds is negative and then goes up to become positive at higher wind speed. And at 90 degrees, the crosswind damping starts off as positive at low wind speeds and ends up being negative at lower wind speeds, at higher wind speeds, sorry. So very good agreement for along wind aerodynamic damping in both directions. The crosswind aerodynamic damping provides insight into the behavior of the tower. And we also noticed that the crosswind damping behavior is similar to that experienced by tall buildings. So that means the crosswind damping could have been dominated by the effects of the spine rather than the lattice sections themselves. For the damping estimation of the cables, we've used the theoretical equation which was developed by Davenport in 1988, which links the diameter of the cable to the mass, to the wind speed, to the mode shape, and the diameter of the cable, as well as the drag coefficient. No instruments were used on the conductors to compare the above expression in terms of experimental values. Values of the aerodynamic damping were obtained to be 7.1, 9.1, 11.8, and 14.8% depending based on the tested wind speed at the wall of wind. So we've repeated the same damping estimation, but now for the entire system. As you can see, the analytical and the single tower, the damping is very low. However, when we connect all the system together with the 6 bundles of conductors and the 3 transmission towers, the system along wind aerodynamic damping is almost 6 times what is only provided by a single tower, and that's due to the presence of the conductors. This is at 90 degrees. Also, the coupling of the tower, insulator, and conductor increased the along wind aerodynamic damping at 90 degrees. For the crosswind, there was also a little increase at 0 degrees for the system, but there was also a little bit of decrease at 90 degrees. So the coupling of the tower, insulator, conductor drastically changed the aerodynamic damping of the system. There was a large increase in along wind damping for both directions, as well as crosswind at 0 degrees. There was a decrease in the crosswind damping at 90 degrees. And coupling is an important aspect in transmission line systems, as noted by previous researchers, and should be considered in the design. Other results obtained from this project include drag and moment coefficients for the lattice towers, buffeting analysis and estimation of acceleration, base shear, and base moment for the lattice towers and the transmission lines, buffeting analysis and estimation of drag and deflection of the conductors for the transmission lines, dynamic amplification factors and gust effect factors for lattice towers and transmission lines, as well as effects of wind direction on mean and peak responses for both phases 1 and phases 2. And those were addressed in 2 journal papers that were already published from this project. The journal papers are Aeroelastic Modeling to Study the Wind-Induced Response of a Self-Supported Lattice Tower, which was published in Engineering Structures in 2021. And we have an Aeroelastic Modeling to Investigate the Wind-Induced Response of a Multi-Span Transmission Line System, which was published in 2022 by in Wind and Structures. We also have an manuscript under review, which is the collaboration between the experimental and the modeling part, which is entitled Revisit of Underestimated Wind Drag Coefficient and Gust Response Factors of Lattice Transmission Towers based on aeroelastic wind tunnel testing and multi-sensor data fusion. And that's also under review and engineering structures. And we have a conference paper that was published in the 11th International Conference on Structural Dynamics, or Euro9 2020. Considering data curation, so that project is available if you navigate to Design Safe, Data, Browser, and Projects. If you search for project ID with a code of PRJ-1379, you will see here in the bottom of the page, experimentally validated stochastic numerical framework, which is the project title, and the project PI, which is Dr. Abdullah Shafuzadi. And if you when you enter it, you head over to the FIU data. If you want the experimental phases 1, 2, and 3, you will get this. I already opened the single tower example, which is phase 1. This is the single tower with no insulators. The data available is the Cobra probe data, which is technically the wind speed at different heights, which you can obtain also from the turbulence intensity and the integral length scale of turbulence. The accelerometer and load cell data, which consists of accelerations, base shear, base moments, and strains, and the cross arms, and also the SAP 2000 models for frequency validation, as you can see there. And also the wind speeds tested for are available in the Cobra probe data with the actual three-dimensional geometry of where those Cobra probes were located with respect to the model themselves and at which height. And the channels and the allocation of the data acquisition system with respect to which channel goes to which instrument is also given in the FIU tests _ ZA. For the instrumentation data, if you go over to the CRIO data, which is the acceleration, loads, moments, and strains, you can see that large file name. So 1 to 50 in the file name indicates the scale of the model, which was 1 to 50. 0.000% and 0.13% indicate the percentage throttle of the wall of wind fans. 00 DEG indicates the wind direction, which is 0 degrees in that case. And T1 indicates that this is phase 1 or the single tower test. You will have T2 as the transmission line of the entire transmission line model, and T3, which is the conductor and the insulator brake. And with this, I'll conclude the experimental part, and I'll give the floor to my colleague, Mr. Ashkan Bagheri Jaddi. Thank you.
Thank you, Ziad. This part of the presentation is mostly done by the team at OSU. My name is Ashkan, and the collaborating authors for this project are Dr. Abdullah Shafizadeh at OSU. Next slide. So the comprehensive tests that were described earlier has provided us with unique opportunities for an accurate assessment of the wind behavior of lattice towers. Every aspect of the test, from the design of the tower, that was a collaboration between the teams at OSU and FIU, to the construction of the aeroelastic model, were performed with the goal to have an accurate representation of the real-world behavior of the lattice tower. The team at FIU has done a great job in conducting a set of unique wind tests, and in the next set of few slides, we will talk about one of the applications to the comprehensive data set that was recorded during the tests. So, wind performance of transmission towers is commonly assessed through high-fidelity finite element models, which capture the incurred damages in the structure. One of the most important steps in this type of analysis is the modeling of wind-induced loads. ASC manuals have provided suggestions in terms of static equivalent methods for wind force modeling. The magnitude of these forces is dependent on several factors, and specifically the drag coefficient are suggested to capture the effects of the shape of the structure on wind forces. ASC has provided a relation for this factor, which is a function of the solidity ratio, and solidity ratio is defined as the ratio of the effective area divided by the gross area of the structure. This ratio, however, does not capture the local changes in the shape of the transmission towers along their height. In addition, the dynamic effects of wind loading are often considered in the design code through gust loading factor or gust response factor in AST manual number 74. But this gust response factor is only a function of the height of the structure and does not capture the unique geometric properties of the transmission tower. So the objective of this study, as one of the applications to the conducted wind test, is to provide estimates of this factor, drag coefficients and gust response factor that accurately models wind-induced forces. So in this study, we have used the data from the following implemented sensors that you can see in this slide: the 6 degree of freedom load cell, the 3 accelerometers on the middle of the tower, and 1 strain gauge. And in addition to the instrumentation installed at the body of the tower, the data from 2 Cobra probes that were installed were used. These probes were installed at the mid height of the tower and the top of the tower. So the data that was gathered during the wind tunnel experiments can be used to provide accurate estimates of wind load parameters. One of the methods that have exceptional capabilities for this task is Kalman filtering. By writing the equation of motion for the transmission tower, in the wind tunnel test, we can transform this equation into the state space form, and from the limited measured responses, we can estimate the responses of the entire system by finding the Kalman filter gain through solving the Riccati equation. And by using the inverse system matrices, we can estimate the applied forces. And to recall, these wind forces can be written in terms of the drag coefficients and gust response factors. Specifically, this method offers the ability to handle noisy data and the ability of data fusion. So as mentioned before, one of the abilities of the Kalman filtering approach is multi-sensor data fusion. The advantage of this approach is that multiple measurements will result in a higher confidence in the estimates. To implement this approach, we have modified the measurement equation with a measurement fusion method, which results in a change in the system matrices as well as the covariance matrix of the measurement noise. And then individual arrays in these matrices can be determined considering the location of each sensor and the type of measurements. Another one of the inputs to the Kalman filtering model is the value of the applied forces to each zone of the tower along its height. These forces are determined using the time history of wind speed at different heights of the tower. However, the number of required observations is larger than the observation points, which are measured by the Cobra probes. For this purpose, we have used a conditional wind simulation using kriging, which provides estimates for the required points. And then with applying all of the introduced modules, such as multi-sensor data fusion, the conditional wind simulation, and wind load identification module, the overall Kalman filtering-based approach is defined as the figure in this slide. So looking at the results of this study, as mentioned before, ASC provides suggestions for drag coefficients in terms of the solidity ratio. For the tested tower, these values are illustrated in this slide. And throughout this presentation, we will compare the estimated values with the ASC suggested values. So for example, the estimates from our proposed approach can be compared with ASC suggestions in the figures in this slide. It can be observed that there is a significant difference across all tested wind directions and wind speeds. And to update the ASC suggestions using the estimated values in this study, we implement a Bayesian regression approach. The benefit of this approach is that without discarding the existing knowledge offered in the ASC manual, we can provide improved estimates. These updated suggestions are illustrated in this slide, and we have provided two sets of suggestions for the data with and without the data associated with the experiments in the transfer direction for the drag coefficient. For this value, for the drag coefficients, model 2 shows a 12% difference between the ASC suggestions and the provided estimates in our approach. Similarly, the updated models for gust response factors show a 13% difference compared to the ASC suggestions. So in comparison with the literature, we have also shown that the model estimates of drag coefficients and gust response factors are not as accurate as the estimates in nodal space. The difference between the modal and nodal estimates of drag coefficients and gust response factors can be seen in the figures on this slide. And another one of the limitations of the ASC manuals is that the suggested values for both drag coefficients and gust response factors do not capture the geometric changes in the shape of the tower along its height. To address this limitation, we have suggested sectional estimates for drag coefficients and gust response factors for the tower. The difference between these sectional estimates and the global estimate can be observed in the figures on this slide. And we can see that the sectional estimates result in a more accurate estimation of the wind load since they capture local geometric changes in the tower better than their global estimates. Furthermore, we have shown the ability of the approach to take advantage of multiple measurements, which in turn results in more reliable estimates. We have also shown that accelerometers are the best set of sensors, which results in smaller discrepancies in the results. And similarly, we have implemented the data fusion approach to estimate the gust response factor of the tower by using a combination of the implemented sensors. So to conclude this part of the presentation, we implemented a Kalman filtering approach to provide estimates of drag coefficients and gust response factor for transmission towers. We used measurements in a set of wind experiments in this approach and suggested code improvements for both drag coefficients and gust response factors compared to ASC manuals of number 7 and number 74 suggestions, respectively, for drag coefficients and gust response factors. So as a reminder, the dataset of the wind test is published on DesignSafe and can be accessed using the links on this slide. There is also a README file that was discussed earlier in the repository that helps understanding the recorded data and its features. Here we would like to thank the team of judges and DesignSafe for this opportunity. We would also like to thank the participants for their time and attention, and we would be happy to answer the questions.
All right, great. Thanks, Ashkan and Ziad, for a really nice presentation. If you have questions, feel free to put them in the Q&A. I see there was one question from Mike Miller that Ziad kind of punted to you, Ashkan. It says the tower appears to be CenterPoint Energy's 138 kilovolt double circuit tower design. Is this correct? Oh, you are muted, Ashkan.
So this the lattice tower that we looked at in this study is actually a 345 kilovolt double circuit lattice tower. Yeah, I think I'm not sure about the CenterPoint Energy part of it, but the other part, that's the voltage.
All right, thanks. Then there was a question, I don't know if everyone online has seen the response to it, but Demetrios asked, the towers of the experimental setup are very light, I assume. Do you think that the accelerometer weight could have affected the natural frequency of the system? And Ziad, you answered that the accelerometers only weigh 2 grams. Did you want to add anything to your response?
Yeah, so most accelerometers are really big. They're used for full-scale tests, and since this is a aeroelastic test where the mass and the frequency are very critical in order to achieve a similar dynamic response between the full-scale and the small-scale model. So we couldn't go with anything that is available in the market. So we got in touch with University of Western Ontario, or Western University now, as it is called, and the team at Windy. Actually, they have their own workshop, and they specifically designed and constructed very tiny accelerometer, 3 degrees of freedom accelerometers that weigh about 2.4, 2.5 grams each, for us to be able to use them on the towers and not violate the mass scaling by a huge factor.
Yeah, thanks for that response. It's an interesting one for me because I did centrifuge modeling at UC Davis for my PhD, and scale effects are always questioned there. Did the sensor cables affect the model response and things like that? I had a couple of questions for you too. The first one is also about scaling, actually. I was just wondering how those conductors were scaled, because like the shape of the catenary curve didn't look the same as real prototype power transmission lines. Were those scaled to have the proper diameter and stiffness and all of that?
Yes. So the conductors, in order to, because I mean the minimum span between 2 towers, the usual span range is between 200 and 600 meters. So we took a span of about 200 meters, and to fit all 3 towers and the 4 spans on the turntable to be able to rotate them and check at different wind directions, the wind effects, we had to use a further horizontal distortion technique of 1/3. So basically what we did is the length, the actual length was reduced by a further 3. So it was 1 to 150. So if it's 200 meters, the cable, the length was about 200 over 150 meters in length. The diameter was increased by a factor of 3 in order to maintain the unit mass per length, and so the drag forces were actually 3 times what they were, in order to maintain them exactly between the model and the full scale.
Right, but then the stiffness of those cables was a little higher, which is why they maintained kind of a downward
Yes, it was a little bit higher because it's very challenging to find like proper copper cables that are, at such a very small diameter. So I think we've used some sort of piano wires for that, if I remember correctly. We ordered them from McMaster, I think. It was like a piano wire with that. They had a little bit more of a warping strength. Their warping strength was a little bit higher. That's why they show that little bit upward bend at some point.
Right. I was curious too about the negative damping, the crosswind damping that you observed. I'm not familiar with negative. Well, actually, we do have sometimes negative stiffness, but negative damping was a new concept for me. So I'm just curious about how that came to be. Is that a real
That's a
thing? Like, are the towers producing energy?
yeah. They don't produce energy. It actually makes. I mean, whenever there's a negative aerodynamic damping, it starts reducing the actual structural damp or the total damping of the system, which makes the response even more violent along that direction because the damping is much lower. So the response and the actual resonance increases whenever you have a negative aerodynamic damping.
Okay, great, thank you. I have just two more questions. I'll keep going. I'm not seeing more in the Q&A, but oh, Mike Miller does have one. Let's see. I don't know if you've had a chance to read this. So he says, interesting presentation. FYI, we would expect to see differences in drag coefficients due to the solidity differences on rectangular towers, such as this model. And then ASE 722 now specifically excludes electrical transmission infrastructure for applied loads. So we refer to ASE 74 edition 4, which uses a slightly different approach, but should produce similar results. In practice, load on structure by itself only represents 5 to 7% of the load. Most load is coming from wires. So there's not really a question there, but I wanted to give you a chance to respond. He was just providing some information.
Yes, that's for the transmission for the system itself. Most of the loads comes from the drag on the conductors themselves. And that's why when you have a snap in one of the conductors, there's an actual imbalance on the cross arms themselves. One cross arm is carrying force and then the other cross arm is not carrying anything. So that's why you have this cascading failure, because actually the left span and the right span of the cross arm, they actually balance each other. Yes, so
Alright.
the most of the tower, yeah, most of the wind load actually comes from the conductors themselves.
Thanks, that's interesting. I didn't realize that. I have two questions too, just about the data. So one is really basic, but I noticed some of your file extensions were TSV. Is that a tab separated value file format?
Yes, that could be opened in Excel. That is a
Okay.
regular Excel file that you can open in Excel.
So that's just like CSV, but using tabs instead of
Yes, yes, tabs
Right,
instead of
okay.
comments. That was our old data acquisition system, which saves them in TSV. But you
Okay.
you can change it to XLS.
Yeah, that's what I
Yeah.
thought. I just wanted
Yeah.
to verify that wasn't like a SAP 2000 configuration file or something.
No, no, no. The SAP configuration files are inside a SAP folder. You need SAP 2000 to be able to open it and run the model again.
To run them. Yeah,
Yes.
right. And then my final question, you presented in the data set, you have the raw recorded data from the accelerometers and wind speeds and things like that. And then you did all this great work on Kalman filtering and stuff like that to derive quantities from the data. And I was just wondering, have you published those data also as kind of like derived data? Because a lot of the time that's what's interesting to engineers, right? They may not want to go and necessarily, I mean, looking at raw data is really complicated, right? That's what PhD students do for their dissertations, and it's a lot of work. So I'm just wondering if there are these kind of derived quantities available too.
Thank you for the question. So we planned so the results that I presented in the second basically part of the presentation are a part of a journal paper that is currently under review. So we plan to publish at least some samples of the code that we used for basically using the recorded data and deriving some intermediate values to capture the drag coefficients and gust response factor in the future. But yes, you're right. I think a lot of interesting observations come up during the analysis of the raw data that you could basically probably not see those by looking at the raw data themselves.
Yeah, I think it's hard for people who didn't conduct the experiments to really effectively use the raw data. But I could see, you know, a lot of other similar tests contributing data to a common database that looks at damping coefficients and, you know, things like that.
Correct.
Okay, great. Oh, so yeah,
ju-
go ahead, Ashkan.
Sorry, I just wanted to mention that this part that I presented is we just basically used the data from the phase 1 of the test, which was on the standalone transmission tower. So as Ziad mentioned, this the data set that is published on DesignSafe has 2 other phases on the transmission line and the transmission line with ruptured conductor and insulator cases. So I mean, I think in our field, data is very important, and we would be happy to see public use of the data by other researchers.
Yeah, that's great. That's why you won the award, right? You did such a good job documenting it and making it ready for everybody. I would just encourage anyone who uses the data, you can push a button in DesignSafe to get a citation for the data set. So in addition, just like you would cite a paper, you can cite the data. And that's a really important thing to do because it has a DOI, and you can now say, I use these data, and it's important. All right, so I think I will wrap up here. If you wouldn't mind stopping your screen share, I'll share mine and show that slide again. So here we go. First thing I'll mention is that, sorry, my computer's a little slow. There we go. All right, so this webinar has been recorded. All of our webinars are recorded and made available. You can find a lot of them directly linked through our Learning Center. So if you go to DesignSafe and click up on the top left on Learning Center, you'll see links to some of them. We don't have links to all of them right there in DesignSafe, but we do maintain a YouTube channel. So you can click on the link to the YouTube channel and go find anything that you want there. And that usually will take about a week or 2 until we can process the video and put it up on our YouTube channel, but it will be available later. We do appreciate your feedback. So here's that QR code. Please take a moment to scan that. We should also just put a link in the chat. I'm not even sure what URL this goes to, but if you can just scan this using the camera on your phone, it'll take you to that survey. And we do use that feedback as part of our ECO assessments. And then I just want to thank Ziad and Ashkan for being here to present to us today. It was really interesting. I really like hearing presentations that are kind of outside of my area, right? So wind effects on towers is not something that I'm an expert in, but I can always learn from experts. So thank you for that. And thanks to Natalie for being here and helping to run this this webinar. And feel free to check us out on Slack if you have questions about using DesignSafe or accessing data. You can post a message there. Somebody will get to it quickly. We also have a ticket system. So if you need help with anything in DesignSafe, you can post a ticket and we'll get back to you pretty quickly. So I think I will go ahead and end it there. And thanks for joining us today, everybody.